Hello, my name is Edmund Martelli, and I have a lesson plan on hydraulic and pneumatic mechanical and electrical theory control valves. The required text for this lesson plan is Andrew Parr's Hydraulics and Pneumatics, a Technician's and Engineer's Guide, 2nd edition. The learning objectives of this lesson plan are to describe two differences between hydraulics and pneumatics, describe a similarity between hydraulics and pneumatics, draw and explain the following diagrams describing its operation: 4-3 spool valve, 3-2 poppet valve, 4-3 rotary valve. Choose 4 of the 5 valves listed below and explain their operation: check valve, shuttle valve, exhaust valve, sequence valve, time delay valve, proportional valve. Explain why solenoids are better suited to pneumatics and pilot valves are very useful in hydraulics. Using figures 4.29 and 4.32, describe two conditions when a linear voltage differential transformer is moved toward the right. Explain how a dither reduces stiction. Explain how current is controlled through pulse width modulation. Explain the following circuits on figure 4.38. Gain, ramp, deadband. Give 2 corresponding inputs to the proportional integral and derivative and explain the output. Explain how to troubleshoot the enable circuit when a light emitting diode is off. Explain how to troubleshoot the current controller when the LED is brightly lit.
Diagrams and symbols.
Hydraulic and pneumatic systems are closed-loop systems. Hydraulic fluid in a tank is pumped to the P-port on a control valve, and it is directed to either the A or the B port. The opposite port returns the hydraulic fluid through the control valve, and it goes from the control valve out the T-port back to the tank, thus completing the circuit. In figure 4.1b, a compressor draws in atmospheric air and supplies it to the P-port of the control valve. The P-port directs it to either the A or the B port, and whichever one is not being supplied pressure relieves the pressure back through the R port on the control valve and releases it into the atmospheric air, thus completing the system. Figure 4.2, you'll notice pictorial diagrams of an extend and retract position.
Diagrams and symbols.
Manual control valves have a handle. In figure 4.3a, you've got 2 positions: retract and extend. In figure 4.3b, you've got 3 positions where you're adding a center or an off position. Figure 4.4 shows those diagrams.
Diagrams and symbols.
So to draw a hydraulic or pneumatic diagram, you begin by lettering a square. For example, in figure 4.5a, you've got a square containing the letter A for a position, either extend or retract, and the opposite function in a square that contains the letter B. In figure 4.5b, you'll notice that 0 denotes the center position. In 4.5c, you've got a normally operated valve. So for example, in this figure C, in position A, you're supplying pressure to the A side of a cylinder, and pressure is relieved from the B side back to the tank. When this control valve is activated by pushing.
Spool valve.
Spool valves are a ported casting containing a spool of round stock that has an inner and outer diameter known as grooves and landings. As the spool is moved through the casting, these grooves and landings either restrict or allow for pressure movement.
Center position.
Center position valves have an extend and a retract function, but in addition, at the center, they can stop a cylinder. This is useful to control a cylinder to stop at mid-stroke.
Rotary valves.
Rotary valves are similar to spool valves, except for that The spool pivots within the casting, allowing for or restricting movement.
Pilot valves.
Pilot valves allow for a lower pressure valve to activate a greater pressure valve. The use of an electronic solenoid is very common. As the pilot valve is opened, pressure is supplied to the control valve, allowing for a greater pressure through a port.
Proportion valves.
Proportion valves use a solenoid, metering notches, and an analyst to provide a rationed pressure force in relation to the stroke of the control valve.
Poppet valve.
Poppet valves have a normal position. The valve stem is hollow and spring-loaded to maintain a seal. As the poppet valve is activated or depressed, pressure is supplied through the valve stem to a port. When the poppet valve is released, pressure again is vented.
Check valves.
Check valves only allow for flow in one direction. Restrictive and throttle check valves use a set screw to adjust how much pressure can be released. These are very useful in hydraulic pneumatic systems when left idle at an extended period of time because they allow the cylinder to maintain its position. When they do not maintain position, it is what is known as creep.
Shuttle valves.
Shuttle valves are like control check valves, but in fact they allow for bidirectional flow. This allows you to hook up multiple devices to a single pressure line.
Fast exhaust valves.
Fast exhaust valves use a flexible ring. They help to reduce system delay time.
Sequence valves.
Sequence valves are similar to pressure relief valves. When one cylinder reaches full extent and full pressure, a second or sequential cylinder is activated.
Time delay valves.
Time delay valves use a reservoir, timing set screw, and a check valve. They also allow for instant relief.
Dither and deadband.
Stiction occurs when a control valve sits idle for an extended period of time. To control this, a dither provides oscillating AC current, keeping the control valve free. Deadband is inherent to control valves. It is caused by the landing on the spool.
Linear voltage differential transformer.
A soft iron core has 3 coils wrapped around it. Notice V sub 1, V sub 2, and a voltage at V sub 3. As the soft iron core is moved, for example, toward the right, the sine wave is inverted, but the voltage stays the same.
Pulse width modulation.
Pulse width modulation allows for a proportioned amount of current flow given time. This allows for a gradual application of current.
Ramp response.
Sudden force creates stress and strain and potential system failure. A ramped response allows pressure to gradually be applied.
Position control system.
Using a LVDT, a phase-sensitive rectifier, and a position controller, the actual and a required spool position can be achieved. Notice the valve has a solenoid and a linear voltage differential transformer. The LVDT sends signal to the phase-sensitive rectifier, which tells the position controller what the actual spool position is. The user inputs a required spool position that also goes into the position controller, and based on that calculation applies current to the solenoid.
Control card.
Control card circuits require 24 volts to the power supply, 10 volts for the manual interface and to activate spool solenoids, and 5 volts for the programmable logic controller. Circuits also contain light-emitting diode indications for troubleshooting. So what do hydraulic and pneumatic systems look like? Let's look at some videos.
That our instructor is wearing safety glasses and she'll work in a safe manner during all of the labs. Now first, she installs a pressure gauge on one of the pressure ports of the manifold. Next, she runs a hose from the pressure manifold to the pressure port of the directional control valve. And what this does, this will supply fluid to the valve and later to the cylinder. Now, she runs a hose from the tank port of the directional control valve to the tank port on the manifold, and this will allow fluid to return to tank after it is used to operate the cylinder. And then she runs a hose from the A port of the directional control valve to the rod end of the cylinder. And this line will supply fluid to the rod end of the cylinder when the cylinder is retracting, and will provide a path for the fluid to return to tank when the cylinder is extending. And finally, to complete the plumbing, she runs a hose from the B port of the directional valve to the blind end of the cylinder. Now this will supply fluid to the blind end of the cylinder when the cylinder is extending and provide a path back to tank when the cylinder is retracting. Now to run the system, first she pushes the button to start the power unit that supplies fluid to the entire system. Next, she shifts the directional control valve in this direction to extend the cylinder, and then shifts the valve in the other direction to retract the cylinder. Notice that the cylinder can be stopped at mid-stroke by centering the directional control. Okay, so what we want to do now is hook up the vertical cylinder using the sequence valve. First, Elise will run a hose from the A port of the directional valve to the in port of the sequence valve, and from the out port of the sequence valve to the blind end of the vertical cylinder.
Done.
Got it.